Good day, everyone. In this presentation, I'm going to introduce you to DBA Bandits, a machine learning agent that performs database index tuning with safety guarantees. And I'm going to show you a glimpse of the huge potential of these technologies have in the area of index tuning and even in the wider area of physical database design. Then you might ask me, why should we care about DBA bandits when you have commercial database tuning tools doing a pretty good job? The answer to that is twofold. Firstly, index tuning is hard, even for existing commercial tuning tools. This fact has been demonstrated again and again in previous papers in this area as well as in our paper. This graph is from 2018 VLDB journal paper by Renata and the others. In this experiment, they have tested with TSP-H benchmark on commercial database system, which they call as DBMSX. To boost the performance of the given workload, they have created a set of indices proposed by the tuning tool of the given database system. On the graph, you can see the execution time after the tuning with respect to the original execution time. Although the performance of some queries got significantly improved, like query 2, there are cases when the performance after the tuning got degraded by several orders of magnitude, like in the case of query 12. So these degradations are due to suboptimal access path choices, which the optimizer favored based on the incomplete statistics and cardinality misestimations. To further understand this problem, let's take a closer look at the example suboptimal access path choice. In this classic example, the optimizer misestimates the number of rows returned from the outer relation in the nested loop join. As you might already know, in nested loop joins, for each tuple we get from the outer relation, we need to do a lookup in the inner relation. Therefore, this is used when we have a small number of rows from the outer relation. However, when you use a nested loop with large number of items from the outer relation, it can quickly lead to performance regressions. As you can see, an execution plan cost is not easily predictable by just using cost model. Unfortunately, these issues can be found even in the state-of-the-art index tuning tools. So if you take a closer look at the index tuning process in practice, normally a DBA provides a representative workload for the physical design tool, which I will refer to as PD tool from this point onwards. And then the PD tool uses its query optimizer cost model to do a what-if analysis. In this what-if analysis, PD tool provides the index configuration and the workload, and the query optimizer will provide the estimated benefit for the given configuration under the specified workload. This process happens for large number of configurations, which will allow the PD tool to pick the best configuration based on the benefit estimates. As we discussed in the previous slides, estimated benefit is unreliable. Second point is seamlessly innocent step of representative workload selection. While it was not very challenging in the past, with modern applications, it's not simple. With ever-growing datasets changing the properties of the underlying data all the time, with ad hoc unpredictable data exploration queries, which depend on the past query results, and with unpredictable changes in the cloud multi-tenant environments, not only the representative workload selection, but the whole index selection process has become much more complex. And DBA Bandits provide solution for both of these problems. And that's exactly why we should care about the bandits-based approach. So let's get ourselves familiar with the multi-arm bandits, which is also referred to as MAB or bandits in short. Getting its name from array of slot machines, bandit is wrapped around the simple idea of pulling one of these arms and observing its reward. The catch is, we can only observe the reward for the played arm and no others. With this limitation, there's always the trade-off of exploration and exploitation. Whether to stick with the best arm based on the previous results or try an underexplored arm to get more information about it. So ultimately, the target of the bandit is to find the sequence of arms to maximize the cumulative reward. What I explained is the basic map problem. There are many map variants as well. What we are interested in is the contextual and combinatorial UCB bandit variant, or in short, we call the C-squared UCB. To understand why this variant is important, we need to understand three main concepts. C-squared UCB is a variant that branches from the UCB bandit, which is based on the idea of optimism in the face of uncertainty, where we strategically explore the underexplored arms where we are not certain about their rewards. Secondly, as the name suggests, C-squared UCB allows the use of context for each arm, providing additional information about the arm and the environment that the learner can observe before taking a decision. What really fascinates me is that given enough rounds, context allows the bandit to predict reward for new arms at the first sight without trying it even once. As you will see in the future slides, this property is very critical for our application to make this practical, even in large databases. Finally, the combinatorial property allows the bandit to pull multiple arms in a single round under given constraints. Again, in the next slide, you will see how this property allowed us to stop combinatorial explosion while staying inside the memory budget. After getting that quick overview of C-squared UCB, let's see how we use the C-squared UCB for index tuning. In the top left corner, you see a new query coming in for the first time, and the bandit observes this and collects details such as predicates, payload, and its execution time before tuning. Based on these predicates and payload, bandit creates arms. In this case, we consider each index as an arm, and the bandit will pick a set of arms each round, which we will refer to as index configuration. This is only possible due to the combinatorial nature of this bandit. Based on the current knowledge and the experience, bandit picks one or more arms for materialization. Here, the sixth index gets materialized. When the same query returns, bandit will again observe the performance after tuning. In this example, bandit observes a 10-second gain in execution time. At the same time, bandit is mindful about the creation cost of the index as well as its memory consumption. Exact reward computation is a bit complex than this, and I encourage all of you to read the paper for more information. With this quick understanding about how we used C-squared UCB for index tuning, let's move to the most interesting part of this talk, experiments and results. Our system was thoroughly tested using 5 publicly available, very well-known benchmarks. In these graphs, you see map performance against a state-of-the-art tuning tool, which we refer to as PD tool. For the completeness sake, we show the time without any secondary indices as well. We have used the datasets with scale factor 10, resulting in approximately 10 GB of data for everything other than IMDb. IMDb dataset has a fixed size of 6 GB, and we have given the memory budget approximately equal to the size of the data in all cases for creation of secondary indices. In the y-axis, you find the total workload running time, which include index recommendation time, index creation time, and query execution time for all 3 components. In the first graph, we talk about the static setting where the workload sequence is known in advance and repeating over time, which is common in reporting applications. In this case, PD tool is invoked soon after the first round with the workload from the first round. In the second graph, we show a random setting where the query sequence is chosen entirely at random, modeling more dynamic settings, such as cloud services. So in this case, PD tool is invoked periodically. As you can see, map performs much better than PD tool under almost all the benchmarks in both settings, except for TCP-H and SSB in the static setting. Especially note that under skewed datasets and complex workloads, map performs exceptionally well. To further understand this experiment, this graph shows the total workload time per round for each tool. And we can see MAP's gradual improvement over 25 rounds to achieve better total workload times compared to the PD tool. We can see large spikes for PD tool at the invocation points, whereas MAP is significantly lightweight. You can notice that MAP convergence is very efficient and effective even under complex workloads thanks to the MAP context, which allow the bandit to predict the reward of new arms without trying them even once. Past efforts have considered more general reinforcement learning for physical design tuning. Due to its randomization, RL can suffer from performance volatility as compared to C²UCB, which is a deterministic algorithm. The above intuition is supported by the experiment with more general RL, where we evaluated the MAP against popular DDQN RL agent. As you can see, volatility of DDQN components are very high compared to MAP. To conclude, I like to summarize the presentation into 5 key points. DBA Bandits is a lightweight MAP solution for index tuning. We use C²UCB MAP variant to enable strategic exploration without pulling all the arms. C²UCB safety bounds guarantee convergence to an optimal choice. By learning from actual query executions, MAP mitigates tuning tool flaws, which comes with optimizer misestimates and unpredictable workloads. And finally, our results show up to 75% improvement in total workload time and 25% improvement on average compared to a state-of-the-art commercial tuning tool. With special thanks to my co-authors, Bastian, Ben, and Renata, I will end this talk, leaving the stage for the questions. Thank you.